Okay, we're going to continue with working with limits for polynomial functions. Those polynomial functions are the easiest limits to work with. So this question is the limit as x goes to 0 from the left. So because the left-handed limit is the same as the right limit, they're the same values, the polynomial functions are continuous. Remember what we're using. The definition of what it really means to be continuous. That's the limit as x goes to a of some function is really f of a. It's functional evaluation. So like we discussed earlier, this would be 5 times 0 cubed now, plus 0 minus 6. And so you just simply use order of operation. Please excuse my dear Aunt Sally. So now you get 5 times 0 plus 0 minus 6. 5 times 0 is 0 plus 0 minus 6. So ladies and gentlemen, the answer is going to be simply negative 6. So I'll put the answer over here. This equals negative 6. Okay, so that the limit as x approaches 0 from the left, because this is a polynomial function, we just use functional evaluation. So this will be negative 6. Now let's take a look here. X is going to 0 from the left. Let's look at the graphical approach because we want to really understand the ideas behind this. So these are the x values. They're going to 0 from the left side. Okay, that's to the left of 0. Those are x values that are smaller than 0. On the curve, though, every x value has a corresponding y value. So as x goes to 0 and gets closer and closer to 0 from the left, we approach this point on the curve, which would be 0, comma, negative 6. So it looks like every one of these dashed lines is a negative number. And the limit answer is always the y coordinate. That's your L, it's the y coordinate value. So sure enough, the graph is consistent with what we see. And let me emphasize again for those who might be needing to review that the function here is 5x cubed plus x minus 6 here. We did the order of operation already. We deduced the answer. So very often we just say, hey, just evaluate the function at 0, plug it in, and yes, we already know this equals negative 6. So we're just looking at this both in terms of the definition of being continuous and looking at the idea here graphically as well. So there's the details for number 7. We got this earlier today. Now, number 8. Another polynomial function. So because it's a polynomial, this function is continuous for all real numbers. It's continuous for the x value being 1. So we can find the answer by using that definition here we just wrote down for you guys. Okay, so let me kind of bring it back down here just to be thorough. All right, you guys have that there? So we take 7 times 1 to the 4th power minus 4 times 1 to the 5th power. Okay, we're plugging in 1 into that function here. That's what they mean by just simply evaluate the function. And by order of operation, please excuse my dear Aunt Sally. Exponents go first, so it's 7 times 1 minus 4 times 1. Which is 7 minus 4 equals a 3. Ladies and gentlemen, there's your limit answer. You evaluated a limit. And this is a two-sided limit because x is approaching 1 that implies we want to look at both the left-handed approach and the right-handed approach. So let's just verify the answer graphically. 1 is over here. So let's approach 1 from the left. Every point on that curve, ladies and gentlemen, is approaching this location here from the left. And then on the right side, x is approaching 1 from the right. It doesn't matter where we stop or start, I apologize. And then all those corresponding points, because for an x value, you get the corresponding y value. You're approaching the exact same location. That address, though, is 1, comma, let's see what that is. This is 1, 2, and that's 3. So we're approaching 1, 3, and again, the limit answer is always the y-coordinate value, or we call that a couple of things. That's L, that's Y, but that's the limit value. So that's what we're looking for on the curve. So sure enough, yes, the left-handed limit equals the right-handed limit. They're both 3. All right. Good job. We got these polynomial functions that work out very beautifully. And look at the curve. It's nice and smooth, and it's nice rolling hills. A beautiful curve. We like those curves. All right, we're back to a linear, which is a straight line, but it's a polynomial. So since our function here is 6x plus 5, this is that function right in here. All we have to do is evaluate the function at the point -4, because polynomials are nice and continuous everywhere, which means polynomials are continuous for all real numbers. We just got to plug this in. 6 times -4 plus 5, which will give you -24 plus 5, and then that equals a -19. So, ladies and gentlemen, the limit is -19 as x goes to 4. And again, we got to check both directions graphically. And I apologize, x goes to -4 from the left. X goes to -4 from the right. So let's take a look here. And I guess we don't have that information, shucks, because -4 is really over here. And so we'd have to approach it. Doesn't look like the graph's there, and I'm not going to kind of get a new graph in there, but whatever. I think you guys have seen enough examples of this to understand what's happening both graphically and really in terms of the arithmetic, and using the definition of polynomials being continuous everywhere. So we got another polynomial there for number 10. This is a nice, beautiful curve. And that function, the polynomial function, if I write it down here, is x cubed minus x plus 7. So this is that function f of x. We can write it as f of x. There we go. So we can evaluate this by simply doing some arithmetic. F of -2. So as x goes to -2, because polynomials are continuous, we just simply have to evaluate this using some arithmetic. Okay, plug this in. Now, be prepared on a test, ladies and gentlemen, to answer these questions without a calculator. Notice I didn't need a calculator for any of these questions. We're just using arithmetic. I don't write tests that you need a calculator. So -2 to the 3rd power, because we're using order of operation. Please excuse my dear Aunt Sally. So we get a -8 minus a minus makes this plus. We get -8 plus 2 plus 7, which will give you -6 plus 7, and then that equals +1. I did not use a calculator. I'm deducing the answers. So the limit as x goes to -2 is 1 for this polynomial function. Let's look at this now over here. So we have -2 here, okay? As x goes, these x values again approach -2 from the left, you are approaching again. These points are going to a location, and then you can't see it so clear. I'm going to erase it, but approach -2 from the right. I want to go through these ideas. Again, these are x values. So on the curve, you're approaching the same location at -2. And it looks like we had to go all the way up here because what you're approaching is this point here. Okay, so every point on that curve here is an x and y coordinate value. So I want you guys to see this graphically. Alrighty, now let me get rid of what we're looking for. So we're looking for the address right in here. Okay, so it looks like x is -2, and notice this. Since this up here is 10, every dash mark is units of 2. 2, 4, 6, 8, 10. So halfway here, half of 2, 2, 4, 6, 8, 10. This is 1. So I just want to kind of really emphasize something that you want to take a look at there, okay? And it's not straight. See if we can straighten it out. Can we? Oh, no. Anyway. Looks like the left-handed limit and the right-handed limit are the same. They both equal 1 because you're approaching from both directions, if you remember. Oops. That's not it. You're approaching from here, from the left, and you're approaching for the right. Every x value has a corresponding y value. So you're meeting at the value -2, 1, and sure enough, that was the limit we talked about. So the graphical approach is verified. But I want to kind of warn you guys, remember, the essence really of this exercise is to recognize that you have a polynomial function and that all you got to do to evaluate a limit is what's called functional evaluation, meaning you're going to use eventually just order of operation for every polynomial, plug in the value, and use PEMDAS. And, you know, that's pretty simple to do. So like on a test, you might not even have a graph to look at. If you look at your homework questions in the book, there are graphs at all. But what I want to do as a lecture and as an exercise is kind of get you ready, I should say, for looking at both perspectives. We got to get a lot of experience here with that. So, all right. Thank you for your time.